So let me make a couple of related remarks. So what's it wanted to say? Okay, so concerning vector fields on spheres. So you look at, so the usual unit sphere in Rn plus 1 is one of the examples which falls in the class of surfaces that you're looking as a and so you consider the case where the sphere is odd dimensional. So so we'll fix notation as usual. So this is all, nothing is new here. I'm just going to write what P is. So this of course sits inside TP Rn plus 1. So I define this associated function by so what I do is look at x, P1, P2, etc. Pk minus P2k minus 1, P2k to be minus P2 P1 minus P2k P2k minus 1. Now the point to observe here is x is a nowhere vanishing vector field, right? So notice that nowhere vanishing vector field sorry suddenly is usually S for the sphere. So why is this so? So you look at the norm of the vector field, because when you look at norm you always look at the square of the norm. So this is xp. By definition, what is this? So this is the inner product of the associated functions. But what is this? So this was the definition of inner products, right, on tangent spaces. So we simply write out what this is. So maybe I just copy and put it here. It's written too elaborately. So minus P2 P1 minus P2k with itself. But what is this? This is just sum of the squares of these coordinates. So this is 1. So the minus signs don't actually matter here. So since so we use the fact that n was 2k minus 1 by noticing that there are an even number of coordinate functions, and so you can pair them two at a time and get this. So you may ask what happens on even dimensional spheres. So on odd dimensional spheres, so here we have seen an example. So we may ask the question, why odd? So what happens on even dimensional spheres. On even dimensional spheres. So, so the famous result here called the Harry-Ball theorem. Perhaps some of you have seen this. Says that there do not exist continuous nowhere vanishing vector fields on even dimensional spheres. Do not exist continuous nowhere vanishing vector fields on even dimensional spheres. So this is a very nice result. One reason I mentioned this at all is to point you out to a proof of Milner of this fact. So there is an elementary. So of course, the usual proofs use the notion of degree from differential topology. So degree of maps between spheres is certain invariant. Yeah. So, but of course, Milner has a lovely paper. So giving an elementary proof which uses only calculus. Yeah. So Milner, of course, great mathematician, Fields Medal winner, but also writes very, very beautifully, right? His books and papers are all very nicely written. So, uh, and analytic. So it is, I think, an interesting paper to read. So uses only calculus and elementary topology, points and topology, right? What compactors, what connectors, etc. of the Harry-Ball theorem, something like this. Maybe it says Brewer's fixed point theorem because you can also do that. I don't remember the exact title, but so elementary proof. So it's an elementary proof using calculus. So it's a good way to exercise some of your several variable calculus knowledge just by reading the proof and trying to understand this. I'll also mention just what there are two main steps here, and I cheat a little bit, but so maybe I write it in the following fashion. So step one, prove the result for smooth vector fields. Step two, approximate smooth vector fields by continuous ones. That's Weierstrass type approximation. So I write it out to point two things out. So and that is, you see, the question is a purely topological one. It only talks about continuous vector fields on spheres. However, and this is the power of calculus, is you use methods of calculus in order to show the corresponding result when your vector field is smooth, and then merely use Weierstrass approximation. So essentially, so mildly adapted to your context, but nothing serious. So approximate smooth vector fields by continuous vector fields by smooth ones. Approximate continuous vector fields by smooth ones. So that's a sort of a nice set of observations. So I'm tempted to say some things more. I mean, how geometry relates to topology, and maybe the power of analysis in all of this for purely topological questions. Yeah. So mm, maybe I'll mention it later. So when we have seen a little bit of curvature, etc., I think I'll come back to this set of remarks and make a couple of further remarks in this direction. So maybe now I will so leave this like that. Um, so we come to the notion of orientation. So, as, so in this case, because again, the hypersurface being codimension one, things are generally easier. Yeah. So if you simply look at smooth manifolds and look at codimension one submanifolds, so this is always a nice setting. So, um, so what did you want to say? So orientation, yeah. So smooth unit normal vector field on an n surface. So this is S contained in Rn plus 1. It's called an orientation. On the surface. Now, so this is all aside. So maybe this whole discussion is a little bit of an aside. So where we looked at was when things are connected, then there are only two unit normal vector fields. So we go back to this now. So when we talk of orientation, so the above result shows that there are precisely two possible orientations on a connected n surface. On a connected, so that's the crucial thing. So of course for us this was path connected. So on a path connected n surface, and the choice of them will give you an oriented n surface, right? The choice of orientation, you fix one. So there are only two possibilities because we restrict our attention to only path connected n surfaces. And making one of those two choices gives you an oriented n surface. So, so we choose one of them. And then call an n surface together with a choice of orientation as an oriented n surface. Okay, so this, of course, brings us to the Möbius band. I will be somewhat hand wavy here, but this is just to show that this is because the Möbius band is, it's not orientable. It does not arise as a regular hypersurface for some smooth function. Yeah, so that's the observation we want to make. So the construction you all know, you take a rectangular strip of paper, you glue them together after twisting one of the ends by 180 degrees. Um, so maybe, yeah, it's somewhat painful to write this in detail. So what is the idea? So maybe I copy the picture from somewhere. I can put that up. So we will look at this whenever. So because of the picture, I can merely point out. Um, so on the Möbius band, there is of course the central circle here. So as seen here, the thick uh, line that is drawn, and you look at these unit normal vectors at some point. So unit normal vector at some point, and you move along the central circle, and because of the twist, you notice that as is drawn here, so this bit, you see that as you go one full round along this central circle, it comes back to the same point, but inverted, right? So there's a sign change which happens. So and that's why this is, so you can't make a uniform choice in a continuous fashion because of the sign change which happens. And so that's why the Möbius band is not orientable. Um, so I think it's easiest to just leave it like that. Of course, this you can make very precise and so on. Yeah? So that's a good exercise to actually sit down and do. Write out this gluing thing as explicit identification between the end intervals and so on. So you can write explicit formulas which give you the, the fact that, which tell you the fact that these normal vectors actually change signs as you go once around the central circle of the Möbius band. Um, so so in particular, you see that there is no smooth unit normal vector field. So this implies that it cannot be expressed as the regular level hypersurface of some smooth function. Yeah. So this cannot be expressed as the level set of some smooth function in such a way that the gradient vector field is non-vanishing. So in that sense, it is not an n surface according to the definition we have. So it's not the level set of some smooth function. So that's just a very informal discussion of the Möbius band. And just to say that because we are looking at regular hypersurfaces, it's a fairly restricted class. Of course, it is a very nice class, but it is important to know that there are nice objects which lie outside this definition as well. So, okay, so maybe let's quickly. Uh, oh, I'm doing badly for time. I see. Um, so okay, so let's look at least take some examples here, even if somewhat quickly. So unit vector a direction at P. Now, orientation, of course, this is just smooth choice of normal directions at each point. Yeah, so this is just to say what direction is. It's just any vector in the full tangent space, yeah, of the ambient space. So that gives you a direction, and orientation is smooth choice of normal directions at each point. So on an end surface, smooth choice of normal directions at each point. So maybe I give the general thing here. Maybe tomorrow we'll look at a couple more examples. So you look at dimension n surface. So what is an orientation in this case? So an orientation really corresponds to a partition so of the set of all ordered bases so ordered basis for each tangent space. So sorry, TPS into two subsets. So one, so there are two things here. One, orientation consistent with the orientation. So basis consistent with the orientation. Another, of course, inconsistent. So what do these mean? So this consistent meaning the if you look at an ordered basis, so maybe I write this in the next page. So consistent here means, so V1 to Vn is an ordered basis for TPS. Is said to be consistent with the orientation of the normal vector, because we saw that orientation is a choice of a normal, unit normal. There are two possibilities because S is connected for us. It's consistent with the orientation given by the normal vector. So orientation given by the normal vector. If the determinant of V1, Vn, and the normal vector is positive and inconsistent if it is negative. Is negative. So maybe in lower dimensions you can write some of this down very explicitly. So if there's, so maybe we'll come back to this a little bit later. So at least wanted to get started with geodesics today. So let me. So is that truly, in some ways, geometry begins? So what are these? We know from popular culture, so to speak, that these are the straight lines, analogs of straight lines on surfaces. Yeah? So straight line in Rn plus 1. So there are several aspects to this. We'll see some of them. So you might have heard of geodesics as being the shortest path which joins points on a manifold, etc. But it's not. So not every geodesic minimizes the distance between points. Yeah, so that is easily imagined by looking at the sphere of, so dimension at least 2, and taking 2 points which are not antipodal. Then there are 2 arcs of the circle between them, of the great circle between them. So one, of course, longer than the other, but both are geodesics, right? So if they do minimize lengths, we say minimizing geodesics and so on. So okay, I haven't said what geodesics are, but I'm saying that just as comment on the general idea that geodesics minimize length, is that this is not true. And the example to always have in mind is spheres. Right. So if you take antipodal points, there are 2 sets of geodesics joining them. One, of course, is of smaller length. Okay. So for this, in order to define this, we need a couple of notions. The first one is that of vector field along a curve. So that's the first notion we need. So along a parameterized curve. So we are given a parameterized curve. So initially we look at Rn plus 1. So what is it? It's a map which assigns to each point in the interval at gamma t. So this may look a bit, odd. Why is one looking at xt instead of x gamma t, right? Um, so part of the reason is, so maybe I write it down correctly. So that is in symbols. So xt belongs to t gamma t of r n plus 1 for every t. So this is what you mean by a vector field along a curve. Notice that it's not just the restriction of x to the curve. Yeah, so it can be, but in general it is not. So we already know examples here. So let me look at a couple of them. So at least one. So let's say one example. So you take a parameterized curve itself. To Rn plus 1. And we consider the velocity vector field of along gamma. Why? So this is just to understand what this along gamma here means, right? So the claim is that the velocity vector field is a vector field along the curve gamma. Why? Since by definition, so this is gamma t, and so d gamma by dt. Yes, of course, we write everything component wise. No? So gamma is gamma 1 to gamma n, and then d gamma 1 to d gamma n plus 1. So, right. So this is the point is gamma t, right? So when we talk of the velocity vector field as being gamma dot t, it means this pair. So the point is gamma t. So your velocity vector field lies in the tangent space to Rn plus 1. So, so length, okay, so we need something about length as well. So of a curve, I mean of a, so you define this as a function from the interval to R. So defined by, so this is just the norm of the vector which is given at that point t. So this is a function along gamma. course, the function along gamma is just a function. Yeah. So along the curve, I didn't say what it is. So this is what a function along. So function f along gamma is just function f itself. So we already saw that the length of the tangent vector field is called the speed, right? So it gives you the velocity vector field. I mean, it gives you the velocity, and so the norm of the velocity vector gives you speed. The as I mentioned the remark here, and that's a nice picture which is given in the book. So let me go back to the set of pictures, which indicates why one considers and that's the key remark in the figure, right? So you may have the image of the curve having self intersections and such things, but so you don't want to so the so vector fields along the curve, so these are defined on the parameter space for the curves, just so that self intersection does not cause problems, right? Because at a point of intersection you could have two different vectors in different directions, yeah? So at the same point, so this we don't want to avoid, so we just look at the parameter space itself. So in practice, of course, so restrictions of vector fields to curves are examples of this. Yeah. So example. The point I want to make is these are not the only ones. Yeah. So example. So the restrictions of vector fields, restrictions of vector fields on, so maybe I should give a name of a vector field x to, so okay, so first of all is of a vector field x on an open subset such that, so maybe I take the restriction out for now. So you consider a vector field x on open set such that the image of the curve lies in that open set. So composition is defined. Then restricting to the curves simply means you compose the vector field with the curve. And this is a vector field along the curve gamma, according to our definition. Yeah. So one more example. Restricting a vector field to a curve actually is a vector field along that curve. Um, now, so we want to say something about smoothness. Uh, so we want to be able to define derivatives of vector fields along curves. So that's the crucial part. So sometimes these are also called covariant derivatives. I'll come to that when we go there. But so let's so we define the derivatives. So define the derivative of a smooth vector field along a parameterized curve gamma by, so Alex, yeah, I think I keep interchanging the order of the arrow and the dot. I think I'm not consistent with that. I should check. So this to be gamma t dx1 by dt at t. So these are the component functions of the function associated with the vector field. You simply take the derivatives of the components there, because xt is just the, you can write it down as components. Yeah, so we call that xt is actually gamma t x1 t xn plus 1 t. So we define the derivatives of a derivative of a smooth vector field along a curve to be this. Notice that I'm not saying dx1 at gamma t. So that's the only observation to make is that. So what does it really do? So this sets us up for the definition of a geodesic. So we can say we know what a velocity vector field is. Now we can say what the acceleration is. So acceleration. So this is by definition, the derivative of the velocity vector field. Right, so recall that the velocity vector field is a vector field along that curve, right? So when you say velocity vector field, you talk of velocity vector field of a curve. We observed earlier that the velocity vector field of a curve is a vector field along that very curve. Yeah, so we have the derivative as defined above, and so we can write it down. So we denote it by gamma double dot, and this is by the definition of derivative above. This is just the so this is just the second derivative if you wish. So because already for the velocity vector field, you have the first derivatives of the component functions, right? So of the curve itself. So here you differentiate that once more. So this is gamma n plus 1 at t. Okay. So again, I will refer to a picture which was in the book. So this is somewhere there. So it tells you what you need to know about acceleration. Right, so this is the derivative of the velocity vector field. So this is how we define this. Now, yeah, so we can say a bunch of things, but maybe I will really stop here. So because another 4 more minutes, and or maybe I'll list. Yeah, so I think I will stop here. so that I can start essentially with defining geodesics tomorrow. So, are there questions or comments? If not, we will start on Monday with the definition of geodesics and calculate examples of geodesics.